In this video, we'll continue our look at the metacircular interpreter by examining the implementation of the abstraction barrier beneath the eval-apply functions. So recall that most things in Scheme are represented as lists, otherwise known as S expressions or symbolic expressions, where the car of that list is the operator and the CDR is the arguments to that operator. So for example, even special forms like if I said something like if equals x0 and then times 3x, otherwise plus 3x, this is it's a special form. It's a valid expression in Scheme that has a value. But if we take a closer look, we can also see that it is just a list that in this case has 4 elements, right? It has the element if, has the combination equals x0, has the combination times 3x, and the combination plus 3x. So a list with 4 elements where that first element has a special role to play as being the function or the operator of the combination. What this means is, in order to implement the abstraction barrier, in order to create a representation of expressions in the Scheme language, all we end up having to do is essentially create a bunch of list processing operations. So let's scroll through these. The first set of functions for this abstraction barrier is a set of special evaluators. So sorry, scrolling back up to eval here. For each of the different special forms like if and lambda and begin, they all have these special evaluation functions. So eval an assignment, eval a definition, evaluate an if. Lambda for some reason is right in the eval statement itself where it has a procedure combination there as well. So what we have here is essentially a bunch of special form implementations just below the apply function, where list of values essentially is it's a mapping operation for all of the different arguments in a procedure application. So list of values is used here in the eval inside the call to apply. So it says take the values of all of these expressions. So if this were a regular function, so if I did that, then these would need all to be applied before we could, evaluated before we could apply f to their values. So that's what list of values does. Essentially, it maps the eval function across all of the expressions in a list. So we have a number of expressions, some environment in which to evaluate them. No operands is essentially just an alias for null. And if you look closely, you can see this matches a very similar pattern to the map function. If we're out of operations, if our list is empty, then we're done. Otherwise, we're going to cons our function applied to the first one to the result of mapping through the rest of them. So in this case, our function is the eval function, this function that we created up here, or that was created for us up here. And the argument to that eval is one element out of that list. So first operand, again, an alias for the car of the list. And then some environment, which is just the environment that we're evaluating these things in. So the past environment. Okay. So we eval that first step, and then we say map or list of values through the rest of them. And again, that's essentially an alias for the CDR of these expressions. So continue on evaluating all of those. Okay, so each one of these special forms needs their own evaluation rules. I'm not going to go through all of them, but to see a few just to get the sense of how this works. The eval if is a way of evaluating if statements. And again, we know the rules for evaluating if statement is evaluate the condition. If that's true, then evaluate one branch. If it's false, then evaluate the other branch. Okay, so in this case, the eval if is actually dependent on the underlying Scheme's implementation of the if special form. But that's going to be true no matter what language you're in, because ifs actually have to be created in the circuitry themselves. There has to be some digital logic that has a conditional evaluation or a conditional jump in the circuit itself. So at some point, we're going to have to break that down. So in this case, we just give it straight to the underlying Scheme's if. But we can still see the steps that are there. So if the condition is true, so we evaluate that condition. So the if predicate here is an accessor for an if expression. So an if expression, again, looks like that. So the if predicate here is an accessor for this expression that says get the second element out of that list. Okay. We pass that into eval to determine its value. It should become true or false. But this true question mark, so I'll just jump to the definition here, essentially just says so long as it's not false, then it's true, which I believe is the same rules that Scheme uses. All the way back, where are we? Here. Okay, so if the thing evaluated here is not false, then we'll consider it true, and in that case we'll evaluate this branch using the underlying scheme's special rules for evaluation for if statements already. And if it's false, then we'll evaluate the alternative. So we have the step-by-step instructions for evaluating an if, but again, dependent on the underlying scheme's implementation. Okay, so we have accessors and we have calls to eval, essentially just structuring things together in such a way that we can walk through the different pieces. A few other evals here. So there's Eval Sequence, which works a lot like a list of values. It essentially applies eval to all of the different expressions inside a list of expressions. Eval Sequence is used for begin expressions, for example, or for the body of a function. So we see that here in apply, where apply says eval the sequence of expressions in some procedure body within some environment. So Eval Sequence essentially just walks through, calls eval on each individual element, and then calls Eval Sequence on the rest of them, so recursing down that list. And if we're out of values, then it returns the value of the very last one. So if this is the last expression, then we're not going to recurse anymore, and we're going to return the value that we get when we evaluate this last expression. Okay. Let's go to Lambda as well. For whatever reason, the SICP puts Lambda in the evaluation rules for Lambda directly in eval instead of into an extra expression. But essentially what Lambda does is it converts the Lambda expression, which looks something like, let's type one out here, something like lambda x times xx. So the name Lambda and then a list of parameters and a list of expressions for the body of that procedure. And what it does is it makes a procedure object out of that. So make procedure is a constructor that will take in a list of parameters and a list of expressions for the body, as well as some reference environment, the context for that procedure. And what it does is it creates the compound procedure object that looks something like what we've seen here, the underlying implementation's representation, the MCI's representation of a compound procedure. So make procedure is going to take in a lambda, eval is going to take in a lambda expression, and we're going to peel that apart. So we're going to take the parameters out of that. So that's this list here. We're going to take the body out of that. So that's this list here. And then we're going to combine all of that with make procedure to get back a result like this. Okay, so lambda, when evaluated, just gives back a procedure object. It doesn't run that procedure or anything. Okay. Eval assignment, eval definition. I think we get the idea for all these. They just have special rules for evaluating each one of these. We'll talk about these more when we actually get to the environment. So setting variable values and define variables. These change the environment structure itself. So I believe once we see the actual environment, these will make more sense. But again, we just have special rules for evaluating an assignment operation. So something like set x to be 4 needs to first find the value for x and then mutate the binding. Define x to be 1, for example, needs to determine, does that already exist? If so, destroy the old binding and replace it. If not, then create a new binding. All right. So let's move on through this abstraction barrier. So that's all the special evaluation rules. But again, there's still some abstraction going on here, right? In order to determine the different parts of an if statement, for example, we need to have these accessor functions. In order to construct lambda, we need to have this constructor operation and these accessor operations. So how do those work? And I think moving forward, that will be more informative. So predicates and accessors. So the first part of this is this self-evaluating, and this is used in our eval function here. So we have self-evaluating, we have variable, quoted, we have all these different predicates that determine what kind of expression are we dealing with. So the first kind of expression is a self-evaluating expression. Jump back to the definition there. We can see this is just as far as the MCI is concerned, anything that's a number or a string, we'll consider those to be constants. Anything else we'll say false. Okay, so it may not have all the possible types of scheme, but as far as we're concerned, these are self-evaluating. Okay, but all of these other ones, all of these other special forms here, variable, quoted, assignment, definition, these are all dependent on this extra function here, tagged list. So we can see quoted here, calls tagged list to see, does the expression start with the word quote? Similarly, where's our if statement? Well, we'll use assignment. Assignment says, does this expression start with the word set? Definition says, does this expression start with the word define? So these all work based on this tagged list function. And all a tagged list does is says, is the first element in a combination equal to the provided tag? Okay, so is it a combination first of all? If so, then return true if the car of the expression matches the given tag, otherwise return false. So if expression is some large combination like this, and tag is the word lambda, then this will be true because the first element, which is this guy here, is the symbol lambda. Okay. Similarly, if it's an if expression, the first element would be an if. So tagged list is just saying, is this a list that starts with one of these keywords? And you can see all the different predicates depend on it. So assignment depends on tagged list starting with set, definition with define. There's if. If is it a tagged list that starts with the keyword if? Okay, so all these different predicates for determining is this the certain kind of expression? And then again, that just boils down to, is it an expression that starts with this keyword? Okay. So the other accessors that are out there, let's not go through all of them because they're all pretty much the same. So let's just use lambda here because it's here. So we have the predicate here for lambda, and then we need some accessors. So a lambda looks like this, right? We have lambda, and then we have a list of parameters, right? We can make a bigger lambda, let's say lambda xy and times xy, something like that. And maybe even display x, new line, and then xy. So we have a lambda here that has 2 parameters and 3 expressions in its body. So if we ran this through just regular scheme, ignoring the MCI, once we actually ran this function, so if we said something like apply this to values 1 and 2, what would happen is it would evaluate all 3 of these expressions, right? Now display and new line are side effect expressions. They don't actually have values. They just display things to the terminal. But then times xy should have a value, and the value of the entire lambda should be the value of that last expression, in this case 2. Okay, so to make all of that work, we've seen how the special evaluation works. We haven't actually seen how, sorry, scrolling to the top here with eval. We haven't actually seen how make procedure works, but we've seen it's dependent on being able to get the parameters and the body out of this expression. So let's jump back down to this first one here. So we have our predicate to determine, okay, this first thing is in fact a lambda, so it's a tagged list starting with the keyword lambda. Check. Well, let's go back to our original lambda expression. So it's a tagged list that starts with the keyword lambda. Now, if we want the parameters, that's this block here, well, that's just the second element of the list. So we just take the CDR, which gets rid of the lambda, so we have the list that has these elements in it, and then we take the car of that, which is the list xy. Okay. Similarly, the lambda body, because it needs to be a list of all of these expressions, of 1 or more expressions, we just take everything that follows the lambda parameters. So the CDR gets rid of the lambda, and we have this. And we take the CDR of that, so the CDDR of the original expression, gives us a list of everything else, in this case, the expressions of the body of our lambda. So notice that the accessors for different parts of an expression, they're just list accessors. We just car and CDR down the list and take the elements that we need. Okay. Make lambda here is a constructor that's used elsewhere in the code. We haven't actually seen that here. Could be useful perhaps on an assignment question though. The idea here though is just creating a lambda based on some parameters in body. So essentially it's given all of this information and it just attaches the word lambda onto the front of that and returns a list of the 3. So it's a constructor that creates expressions, again using list processing operations. All right, let's talk about ifs because ifs are pretty straightforward when it comes to dealing with special forms. We've been looking at this example a little bit already. So we have the if predicate, which determines is this expression an if statement, and again that's just dependent on tagged list. Is it a list that starts with the keyword if? So let's type an if statement here. That's fine. Okay, let's type in an if statement. So if, what was our if statement before? If x equals 0, then plus 3x, otherwise times 3x. Something like that. So it's a list that has 4 elements. And it's always going to be exactly 4 elements with an if statement if it's going to be a well-formed if statement. The first element is the keyword if, so we have a predicate for determining that. If we want to know the condition, which is called the predicate here. This is the second part of the if statement, so it's just the catter of the entire expression, right? We drop the car of our list, we're left with this, that's the CDR, and if we take the car of that, then we have the condition. Okay. If we want the true branch, the then branch as it's sometimes called, the consequent, so that's the CA DDR. So we CDR down twice, so we get rid of the if, we get rid of the condition, and then we're left with this. And if we take the car of that, that will be the first expression. Similarly for the else part. Now the else part's optional. You could just have an if statement that looks like this with 3 expressions. So first determine is it there. So if it's not null, then take the CA DDDR. So CDR down 3 times, get rid of those first 3 elements, and then take the car. Okay. If it is null, then we'll just return false. Okay. So this is the basic idea behind the abstraction barrier that built up all of this eval apply steps, right? So for pretty much all of these, we had some sort of predicate, determine is this some kind of special form? And if so, then we'll walk through the special rules. And we saw those special rules largely depend on accessors. We want the consequent or the alternative of this if statement, or the predicate part as well. So it just lets us get the different parts out of these lists, and the entire abstraction barrier now is dependent on these well-named functions rather than these list operations. As you can imagine, if we didn't have this abstraction barrier, so imagine just trying to write eval, and this line alone, without using the predicate if or the eval if functions, will become quite unreadable, right? You'd have to determine, is the car of the expression equal to if? And then if so, then you'd have all of essentially this logic, but instead of eval predicate, instead of predicate, consequent, alternative, you have eval the catter of the expression, eval the CA DDR of the expression, or eval the CA DDDR of the expression, which in that small example maybe doesn't seem terrible, but as you can imagine, trying to write this entire thing with cars, catters, and CDRs would become quickly unmanageable. So we have an abstraction barrier that simplifies all of this thing, or all of these things. So let's scroll down to get through. I think that's pretty much all the important ones. We have assignment operation, which again does the same thing. We have a set expression, that's set x to be 1, let's say. We have accessor for the variable, the x part, and an accessor for the value, and that's just catter and cadatter again. Same with define. With definition actually is an interesting one because there's 2 different forms for define, right? We have, let's say, define x to be 1, creating a variable, and then we have define, x to be 1, creating a function. Okay. Now in this case, I created a very weird function, a function that was called x that has no arguments and just returns the value 1. So maybe not very useful function, but we have 2 different forms of define, one for creating variables, one for creating functions. And the definition of the abstraction barrier for defines matches that duality. So we have our predicate that determines, is this thing just a list that starts with the keyword define? Can I get this up high enough to see those examples at the same time? There. So here's our 2 examples, define x1 and define x1. In both of those cases, we have a combination that starts with the keyword define. So the predicate doesn't have to change depending on which form you're using, so we have one predicate. But if we want the variable, right, in both cases you're creating a binding, so there's always going to be some sort of variable name. If we're dealing with just the regular symbolic abstraction, just creating a constant here, then the catter, the second element in our list, is just going to be an element. It's just going to be a symbol. So we can ask if the catter is a symbol, then just return that symbol. If it's not, then we're dealing with this define form. And the define form is going to have essentially a list here at all times, right? It's going to have bracket, the name of the function, a list of all the different parameters, and then a close bracket. So of those 1 or more symbols, we want to take the first symbol, and that's what this is saying. So the CAADR of our expression. So if this is our entire expression, we take the CDR of that, so that gives us this. We take the car of that, so that gives us this list, which again may have more than one element. If I said something like define f of x, y, z to do plus x, y, z, let's say. The CDR gives us all of this. The car of that gives us this list, but from that we just want the symbol that we're defining, just that f. So we take the car of the CDR. Similarly, for getting the value out of a definition, we first check, is this thing a symbol? So are we dealing with this older form defined, this simpler form to define? If it's a symbol, then we can just return the next element. Okay, that's going to be the value part of this expression. We still need to evaluate it, but it's the part where that value would be. If it's not a symbol, then what we need to do is make an entire function out of the different pieces of this define. So we call make lambda, which we saw was essentially just consing the keyword lambda to a list of parameters and a list of expressions. So this needs to be a list of parameters, and this should be a list of expressions. And now we have cdr and cdr, and you can already see just by having it like that, it's not as obvious as it might be. So the value part, let's go down to this combination here. So if we want the list of parameters, that's going to be the list x, y, z, sans the f at the front. So that's this. So take the CDR, which says get all of this, so drop the keyword off the front. Take the car of that, so just the combination, the signature combination here. And then we don't want the f in that one, just the remaining parts of that combination, so we take the CDR of that. So just the x, y, z. So that gives us a list of parameter symbols. And then we also want the list of all of the expressions, which remember, might be one, might be more than one. We might have some displays or whatever are also in there. So in that case, we just take the CDR of the entire expression, which says take that, and we take the CDR of that. So that's if there's one or more expressions here, we're going to return all of them as a list. Okay, so define again has two different forms dealing with the two different types of defines that we could use. Okay, scrolling. So we have cond and if. We don't really care about them too much. I'm not going to talk about cond very much. Suffice to say, you might recall at the beginning of the course when I first mentioned conditionals, I said a language can get away with only having one or the other. If it has an if statement, it can make conds by creating a bunch of nested if statements. If it only has a cond, then it can create if statements by essentially having a cond that only has one or two branches. So in our MCI, we have if statements implemented, and all cond expressions will actually be converted into if statements. So I'm not going to walk through this expression because it's a bit time consuming, but the idea is it takes the cond expression as we've known them, so cond, some condition, some result, some other condition, some other result, and essentially creates a bunch of nested if statements. So recursively calls make if by pulling different parts of the cond apart and attaching them into one large nested structure. All right, begin and sequence, they're just evaluating things over and over again. They all work the same. If we have some sort of combination, we have ways of accessing those combinations through cars and CDRs as necessary. Anything else I need to say about this? I think they're all pretty similar from then on. Yeah, okay. So, given some representation of an expression, so some S expressions or lists, we can figure out what kind of expression that is. So we have predicates for determining the structure. So is it an if or a cond or what have you, which is really easy because we have Lisp's prefix notation. So we essentially just take the car of that combination and say, does it match one of these tags? We can access the different parts of that expression, essentially just using different list accessors like catter and what have you. And then we've seen how all of these things can then be used to evaluate the special and even the non-special forms. We just need accessors for the different parts of these lists, and then we can use those parts as necessary in their special evaluators. Now, all of this is done within the context of some environment. So in the next video, we'll take a look at how the MCI structures, defines, and uses that environment. I'll see you in the next video.